Have you ever looked at a complex molecule and just seen, well, an impossible puzzle? We're going to change that. Today, we're looking at organic reactions not as some abstract formula you have to memorize, but as what they really are, a powerful, hands-on set of tools. This is the chemist toolkit for building pretty much anything.
So that really gets to the heart of it, right? How do we actually build the molecules that make up our medicines, our materials, even our own bodies? It seems impossibly complicated, but the answer? It's actually surprisingly simple. And here's the secret. It's not about knowing thousands of random reactions. It's about really, truly understanding a handful of core moves. These fundamental transformations are the building blocks chemists use again and again. You master these, and you've basically learned the language of how to build molecules. All right, let's open up this toolkit. We're going to start with one of the most basic and useful operations there is, just swapping one part of a molecule for another. We call these substitution reactions. Honestly, the best way to think about it is like a game of molecular musical chairs. You've got one atom or group sitting in a specific spot, and another one comes along and just takes its place. It's a clean, direct swap. Simple as that. So let's see this in action. This is a super common substitution called an SN2 reaction. Here, our goal is to attach that new piece with the nitrogen to our starting molecule. To do that, the oxygen atom from our molecule acts as an attacker. It comes in, kicks out that chlorine atom, and snaps right into its place. See? A perfect, direct swap that builds a brand new bond. And this swapping tool isn't just for simple chains. It works on these incredibly stable ring structures called aromatic rings, which are, the backbone of a ton of medicines. In this case, a nitrogen atom swoops in and cleanly swaps places with the fluorine atom on the ring. Now, what makes that possible? It's that powerful NO2 group there. It acts kind of like an electron magnet, making the ring much more willing to make the trade. It's a great example of how chemists can strategically set up a molecule to make these tools work perfectly.
Okay, so we've swapped parts around. Now let's grab the power tools from our kit. These are the reactions that totally change a molecule's properties by playing with its electrons. We're talking about redox reactions. Redox is really two reactions working together, oxidation and reduction. Think of it like a control dial. Oxidation dials the power up by adding bonds to oxygen, and reduction, that dials the power down by removing oxygen or adding hydrogen. They're two sides of the same coin, and they give chemists amazing control.
Let's check out an oxidation. On the left, we've got a sulfur atom connected to a couple of carbons. Then, after we react it with an oxygen, boom! Notice how an oxygen atom is now attached directly to that sulfur. We've just powered up that part of the molecule, turning it into something called a sulfoxide, which has totally different chemical properties.
And here's the flip side, reduction. We start with that powerful NO2 group we saw a minute ago. By using a little hydrogen gas and a palladium catalyst, which is just there to help the reaction along, we completely strip off both oxygen atoms and replace them with hydrogens. We've effectively powered down the nitro group into an amine, which is an incredibly useful building block for all sorts of other things. So, just to lock it in, oxidation means more bonds to oxygen. Reduction means more bonds to hydrogen. They're the yin and yang of this toolkit, giving chemists fine-tuned control over how a molecule behaves.
So we've seen how to swap parts and how to tune their power level. But to build something really complex, you have to be able to connect different pieces together. And that's what our next set of tools is all about, forging new bonds. And some of these connections, they're more important than others. This reaction here is called amidation. It forms something called an amide bond. And get this, that is the exact same bond that links amino acids together to make every single protein in your body. It is literally the fundamental Lego brick of life.
Here's another absolute powerhouse of a connector, sulfonation. This reaction creates a sulfonamide group, and that group is the core structure of an entire class of antibiotics, the sulfa drugs. This one connection, this single tool in the kit, has saved countless lives.
And the toolkit goes deep. Beyond making amides and sulfonamides, chemists have reliable tools for forging esters, for adding new carbon chains onto nitrogen atoms or onto oxygen atoms. Each one is a specialized connector designed for a very specific job.
So how does this all come together? Well, masterpieces aren't made with a single brushstroke, right? And complex molecules aren't made in a single reaction. They're built through a logical sequence of simple steps.
Okay, take a look at this. We start with the molecule on the left, and through a series of steps, we turn it into the completely different molecule on the right. This whole process is called a synthesis. So let's break down how the tools were used.
First things first, we only want one specific part of the molecule to react. So in step 1, we use the tool to protect that amine group, the NH2. Think of it like putting a temporary cap on it so it doesn't get in the way. Okay, now that it's safe, we can move to step 2. Here, we use a reduction tool to change the ester group on the other side of the molecule into an alcohol. It's a beautiful example of using 2 different tools in just the right order to get what you want.
Let's look at another one. This is a workflow you see all the time. We've got our starting material on the left and the product we want to make on the right. Let's see the sequence of tools the chemist chose to get from A to B.
First up, we use one of our connector tools in a reaction called N-alkylation to attach that new carbon chain right onto the nitrogen atom. Then, in step 2, we use a reaction called hydrolysis, which literally means breaking with water, to just snip off a piece of the original molecule. This unmasks the final product we were aiming for all along. So you see, it's a strategy. Add a new piece, then do a little cleanup.
And this really gets to the core idea. When you look at a complex molecule like this one, don't see an impossible puzzle anymore. See it for what it is, a finished sculpture. It was built piece by piece through a logical sequence of simple, understandable steps, all pulled from this same chemical toolkit.
So there you have it. We've just unboxed the chemist's toolkit for building molecules, swapping, tuning, and connecting. These fundamental reactions are the language chemists use to build and shape our world. So the only real question left is, now that you understand the tools, what will you build?